I think I can start now. So today is our final lecture, and finally we get to a topic which is more relevant to the key mystery of the deep neural network, that is about its generalization. As I've told you about, so the generalization puzzle is kind of the most prominent problem that's there. It is proposed by Leo Breiman at least as early as 1995, and till now it's like 30 years, and we haven't been able to solve it. And now, so we did not really start by looking at this kind of generalization problem directly. However, after all these phenomena, all these kind of preparations, it's time to get into this problem. And also, we can now forget about all these existing framework that we could use to talk about generalization theory, but just think about what kind of generalization description we could have based on all these solid phenomena or solid understandings we have for this system. Okay, yeah, it is our last lecture. And still, condensation is a key phenomenon that inspires all these new understandings of the generalization. Okay, and first, so since we observe this condensation phenomenon, we know that there are conditions for condensation, right? And then there's a natural question is that since I know by tuning the scale of initialization, I can obtain I can let the network in a regime with stronger condensation or less condensation. And then we ask the question, what is the real advantage of generalization advantage of condensation? In what kind of situation condensation really brought about benefits on generalization? But when we think about this problem, we always need to keep this no-free lunch theorem in our mind. That tells you, okay, you shouldn't expect a theoretical argument that tells you, okay, condensation is always good. There's no way we could arrive at any conclusion like that. Therefore, all we are trying to say is that for what kind of problem or what type of problem condensation could really help. So that's the question we should really ask. Okay. And then there are basic observations we could make. For example, we know that the condensation can help us avoid this type of overfitting, meaning that using this kind of highly oscillatory pattern to fit this training data, because that would require too many groups of neurons, right? And far more than the minimum number of groups you could ever use to interpolate this function. Okay, so you could easily observe this kind of phenomenon. Okay, and what's more we can say about the condensation? Yeah, so we can see if we just think about, okay, this type of relatively smooth interpolation of all this training data, and also frequency principle is enough to help us understand this kind of a non-overfitting behavior. So in which sense condensation give us kind of more benefits regarding the generalization? And that's a question we really want to understand. But before we go into the details, I also want to, why is it? I also want to tell you in which sense this kind of generalization issue, or what kind of problems we really have about the generalization that is relevant to the large language models. And we can see there's a very important paper which is called Scaling Laws for the neural language models by OpenAI in 2020. How many people have ever read this paper? Anyone? Then I could say you are lagging behind. So this paper is the most important paper in AI that really tell us, okay, there are 3 factors that are key to the performance of the large language model, which are the model size and the data size, and also the computation you use for the training. And why this paper is so important? Because we know that these neural networks are largely a black box, right? And there's no theory that really predict what are the most important factors for its performance, right? We don't have this kind of theoretical arguments or actually a solid understanding. Therefore, the only thing we can rely on is kind of very careful experiments, right? And it is in this work, the OpenAI, it compared so many different kind of factors, right? It tuned lots of different things in order to find out what are the factors that are the most important for the performance of the large language models. And then we find out, okay, there are 3 factors. So what's the relation between these 3 factors to the performance, right? And it has this, for example, particularly regarding this training data size, it says if I increase the training data size using this as x-axis, and then here's a testing loss, and then there's we can fit this power law relation. So these are in the log-log scale, and there's a kind of looking like a power law relation between the test loss and the data set size. And how they set the other factors. They set all the other factors such that they are not the bottleneck for the realization of these performance. For example, I fixed the 10 to the 8th. Okay, so I said, okay, I want to make the neural network achieve the best performance of the neural network regarding this 10 to the 8th training data. So therefore, we use a really large network because we know the larger it looks to have a better performance. So we use a really large network, and we make sure we made enough computation. For example, we train it sufficiently long to obtain the best possible testing error for the evaluation here. And then that's the curve we obtain. Okay, it says as long as you have more data, and then your performance will gradually kind of become better and better. And why I kind of show this picture here? Because from this picture, you can have 2 predictions. For the one side, if you are able to make a larger and larger data set, and then if you can tune really well, and then you can keep getting better performance. That is what people do in the past few years, right? Keep increasing the size of network, keep increasing the size of the data set size, and also improve the computation power. However, last year in the NeurIPS, the Ilya said, okay, so we're getting to an end because there's only one internet, right? We have used all the data in the internet. Therefore, regarding this data set size, we are kind of, there's no room to actually further improve, or it's kind of really slow to improve that. And then what shall we do in the next few years to make better use of this data, right? And what does it mean by make a better use? If I design an algorithm or kind of a network architecture that kind of shift this scaling, right? And that means with the same training data, we get a much less testing loss. Or if we're requiring, for example, certain level of testing performance, then we require a much less data set size. So that is called the sample efficient issue. We really want some algorithm that is more sample efficient. Therefore, it uses all these data from the internet. It gives us much stronger performance on all these kind of problems. So sample efficiency here is really important issue, and we are facing that. We are trying to devise all these kind of different new algorithms. For example, also reinforcement learning, as we see in the kind of like DeepSeek, R1, or these kind of try to use reinforcement learning to further improve the performance, but with the existing data. Okay, the sample efficiency. And then, is there any intuition that for certain target that the condensation could improve the sample efficiency? Okay, so and it's easy to find the following case where if our target function can be really expressed by a narrow neural network function, and then we can ask the question, how many samples are required to recover this target? And then we can think about the case where we use a wide network. And initially, if I just tell you, okay, I have a model, this wide network, which has 24 edges, which means 24 parameters, I ask how many samples you should provide for this model to recover a target. I think probably you should say at least 24. In that way, you feel a little bit safe, right? However, if you have the understanding that probably it can be expressed by a narrow network, and then you also know this network can condense to a state which is equivalent to that narrow network automatically through the tuning of this hyperparameter, for example, small initialization. And then you have a new expectation. Your expectation is like 12, okay? You say, okay, if I'm able to make the network condense so well, then I think 24 is just too many. Maybe 12 is already enough for us to recover this target. And then, so this 12 become a sample size, which is kind of optimistic in the sense that we say if we are able to tune a hyperparameter to help it condense so well. If not, if we cannot make neural network condense so well, then how many samples we require? Probably still at least 24, right? It's unavoidable. Okay, so that's a general idea or general intuition about for what kind of targets the condensation may bring us some real benefit. And then, so we are going to talk about what is the optimistic estimate of the sample size. So it's try to address the following question. In the best possible scenario, what is the sample size required for fitting a target function in a neural network function class? Okay, before everything, I just want to ask the following question. How much time required from Nuremberg to Frankfurt? 1 hour? 3 hours? Yeah, and what are other answers? Yeah, take a bus, yeah. But now, let's ask the following thing. What is the worst possible estimate to get to Frankfurt? I'm asking about the worst case estimate. How long? Never? Oh, never. Yeah. But maybe you see never is too words, right? Any kind of better estimate? So you see there's this 48 hours by work, right? There's this kind of estimate by this Google, right? What it says, okay, think about the situation. We are kind of in a situation where all these kind of transportation were shut down by certain kind of force. And then we have nothing to rely on but just use our feet, right? And then probably this worst case estimate is actually useful to think about the case because otherwise you don't bring enough food and you didn't get to Frankfurt with enough food, right? And so that is the worst case scenario. But what is the best possible scenario? Anyone knows what is the shortest possible time? Yeah, actually by flight, it's 45 minutes. Yeah, because I just took a flight from the Frankfurt to the Nuremberg, and when I go back, I still need to first take a flight from Nuremberg to Frankfurt, and it's about 40 to 45 minutes. That is the best possible scenario, okay? And then in this problem, which scenario or estimation of the time at which scenario is more close to practice? I would say, actually, so sometimes the best possible scenario is more relevant in a sense that if I'm really in a hurry, right? I don't want to waste any time. And then I probably just choose this best possible. But if I remove the condition of possible, I just let you think about the minimum time required from here to Frankfurt. Just forget about the possibility. What could be the estimate? Yeah, so I'm asking about the best possible, means there's some way we can realize, right? And then you say we can take a flight, and using like 45 minutes. And then I remove the condition that you don't need to think about the possibility. Just talk about the farthest, the shortest time that may be required. I say less than 1 second by light, right? That's the best thing, right? That's the best thing from the fundamental. The first principle tells us you can never arrive there faster than light, right? And that's the best thing. However, you have no means to really realize that. And therefore, you can see that the optimistic estimate is kind of balanced from two sides. The first side, you want to have some best estimate because you know that in certain situations, the best thing could, you could actually get close to the best thing. And why in neural networks we may require this kind of best kind of thinking? Because we really tune all these hyperparameters, right? Whenever I give you a problem, I give you a data set, right? Do you just blindly choose everything and then say, okay, it does not work? No. You always tune all the parameters so that you choose a setup of hyperparameters so that it achieves kind of the best, right? And then you report to the people, okay, that's the accuracy we obtain. Therefore, it's like you try everything, but still you always stick to these kind of shortest kind of, or the best performance, or the shortest time, and then you tell people that is the performance I get, okay? So just using this kind of example, you have an idea of what is kind of the optimistic estimate we really consider. And then there's also some intuitive kind of understanding. For example, yeah, so we are, this is like a graphene or kind of carbon. And then we are asking the question whether it's possible to turn this into a diamond. Yeah. So, okay, in the kind of a worst case kind of estimate, you say it's impossible because you should do that in a very high pressure, very high temperature that is usually not able to create that kind of environment. But if you think about the best possible scenario, then you can actually achieve that, right? You can create an environment to achieve that. But if I ask to estimate optimistically whether it is possible to turn a copper into gold, right? And then you say, okay, even in the best possible scenario, it's impossible through chemical reaction, right? But you always know there actually, if we remove the thinking of possibility, there are certain ways with this nuclear reaction that probably, right? But no one really tried to do that, right? Okay, so that is the some intuitive idea of the optimistic estimate. And now let's go to the concrete problem and the concrete setup. So here's a minimal setup we consider for this sample size estimation problem. So the training data, we just have n samples from a target F star. And we know that this F star is actually, or can be expressed by the neural network we use. That's a basic assumption. And then the model is a neural network. So how we think about that? We think about the neural network here as a mapping from the parameter space to the function space, right? That is very important view we adopt here. And therefore, when I put this f here, I always first put this theta here. And once I get a theta to this f, I get a function. And then we can evaluate this function at a certain point xi. So the reason I'm adopting this view, so I think probably you will see better later in the later part. Okay, so here is the empirical loss function. It's just L2. There's no mystery. And then we just run the gradient flow. And then we ask a problem, given this f star belong to the function space, how many samples are required to recover f star in the best possible scenario? So that's a question I try to answer. And then just think about if this f is really a linear model, so what could happen? So for example, this f theta is just a polynomial model. So think about the case where it's a kind of just a linear polynomial. Therefore, this capital M equals to 2. And then how many samples are required? I think clearly 2, right? Yeah, if it's just a linear, you have 2 kind of coefficient. And without 2 samples, right, you cannot exactly recover the target. So therefore, this problem can be perfectly addressed with like the freshman level freshman level mathematics, and to answer this question. However, just by turning this capital F to a neural network, to a nonlinear model, these problems have never been addressed before. Okay, we don't know the answer at all. Okay, the difficulty is we can always say, okay, there's a high dimensionality, okay, it's a nonlinear training dynamics, and the loss landscape is non-convex, and all this kind of difficulty, we say, okay, we don't know, or we are fine with that. But yeah, so let's see intuitively what kind of result we can actually obtain. So if we consider this still the same target we talked about before, and then we have 3 different kind of models, right? The one model has the same complexity with the targets, and the neural network B and neural network C has more parameters or more complex than necessary. And then we ask, which model should you use to fit this target? Or which model you could expect the best performance, right? And then since we care about the sample efficiency, we ask how many samples you actually require to recover. And the classic estimate is I just count how many independent degrees of freedom in these models. And therefore, for the first model is 12, and for the later 2, both of them has like 24 parameters. Therefore, that is a classic estimate of sample size required for fitting using these models. If that's the estimate that reflects what happened in practice, then our conclusion is we should never use larger network unless necessary, right? And then that is conclusion we obtain. However, all these empirical results does not support this result. All that empirical results tells you, okay, don't worry about using large networks, right? Okay, so at least if you say all these large networks are not good, that is not relevant to practice. And yeah, but I've said before, if you know the phenomena of condensation, and you have expectation that it's possible to make this network C condense so that it is equivalent to neural network A, and then it enjoys the same sample size estimate, but in an optimistic sense. Means that if there's no condensation, then this estimate is irrelevant, right? But with the idea of condensation, you know actually this 12 could be more relevant. Therefore, if with this kind of idea, you say by increasing the width of the network, probably the sample efficiency does not go down or does not deteriorate. And that's really a good news, right, for us. Okay, so you all see these kind of pictures about condensation, and I will skip that. And yeah, so it's just the same thing. So you think about how the network can condense to a really simple state, and then the classic estimate gives you the optimistic estimate in this new setup. And now let's go into the formal mathematical formulation of this optimistic sample size. So first of all, the key to establish all these mathematical definitions of optimistic sample size rely on a quantity that can quantify the extent of condensation. So what is that quantity? So actually, it's not easy to find that, but later we find that this model rank seems to be a very good candidate. So what is a model rank? So just think about the neural network as a mapping from the parameter space to the function space. And then for this kind of mapping, we can take its derivative and then compute its rank. So this kind of a notion actually is common in the differential topology. And then if you are not familiar with differential topology, then here we provide a kind of more direct definition that tells you, okay, you're given some theta in the parameter space, and then you take the partial derivative. By taking the partial derivative with respect to certain theta I, you get a tangent function that tells you, okay, if I perturb this theta a little bit, what is a change in the function space? Okay, so that is this we call tangent function. And then how many tangent functions we have? We have like capital M, right? Because each parameter we can perturb a little bit to see the change in function space. However, is it necessary that all these tangent functions are independent, linearly independent? The answer is no. Particularly for neural networks, if all these neurons are the same, then their tangent functions could be highly correlated. Later you will see. So the model rank here is just to span all these tangent functions and then compute its dimension. So it's just asking the maximum number of linearly independent tangent functions. So that is about the model rank. So the intuitive understanding of this model rank is that it tells you the effective degrees of freedom around theta, or in the tangent space of the theta. So you see, in the theta space, around any theta, there's always capital M. That's a number of degrees of freedom around theta in the theta space. However, because there's a mapping F that maps the theta space to a function space, I ask around this theta, what is the effective degrees of freedom in the function space, right? And then you see you need to compute the number of linearly independent components in all these tangent functions. And then you know, okay, even although there are lots of degrees of freedom in the theta space, you are allowed to perturb. But actually, if you look at the function space, their degrees of freedom are kind of limited, right? That is a possible scenario. So this is a model rank. So in which sense the model rank is relevant to condensation? Let's look at these very simple cases where we have a 2-neuron network with only 4 parameters. Therefore, we can compute everything just easily. Okay, so how to do the model rank? We first take partial derivatives with respect to all these kind of 4 parameters, and then we got 4 tangent functions, right? And the first is we take partial derivative with respect to A1, and then this is the tangent function. And then the second term is tangent function in respect to W1. And then the third and the fourth, the 4 tangent function. And then we ask, like, what is the maximum number of linearly independent functions there? If it is condensed, what does condensed mean here for this tangent function? It means W1 equals to plus minus W2. In that sense, 2 neurons can be combined into 1 neuron, right? If that is true, that means the first 2 tangent functions are the same as the later 2 tangent functions, or they are correlated with the later 2, right? Therefore, this rank will be less than or equal to 2. However, if these 2 are not condensed at all, means that there's no way to combine these 2 neurons in 1 neuron. That means W1 does not equal to plus minus W2, not equal to 0. And also this A1 and A2 are not 0. So that there's no way to combine them. Then R theta equals to 4. So that is conclusion. So the general idea I want to convey here is that lower model rank means stronger condensation. And that is an observation you could have. OK, and let's look at the formal definition of the optimistic sample size. So whenever we have certain f star, this target, this f star belonging to this, the function space of the network, and then what we do is to minimize over all these we call the theta in the target set. What is a target set? It is the inverse of this f regarding this f star. But remember that there may be multiple theta corresponding to same f star, right? And therefore, this inverse gives you a set in the theta space. Therefore, this is actually the target set, which means a set with a 0 generalization error. So this is target set. We search over all the target set to find a theta with a minimum model rank. So that is what we do. And that minimum model rank gives you the optimistic sample size regarding that target function. And that is process. So, OK, it says in all these theta, we find the point with the strongest condensation. And then we ask, OK, how many degrees of freedom we have around this point with strongest condensation, but at the same time with 0 generalization error? What's the degree of freedom? It tells you, OK, just this OF, right? And then, based on this understanding, you know, if our global training is lucky enough to guide the training trajectory to the neighborhood of this best possible theta, and then just need this number of samples in order to finally converge to these target. OK, so that's a basic understanding. Later, I will come back to this argument a little bit later. But here, there's a kind of very elegant mathematical definition of the optimistic sample size. Therefore, you should know that it's possible just from this definition, we can compute like the optimistic sample size over different targets in the function space. And then, just to give you a picture. So previously, when we think about using a model to recover a target f star, right, you are always stick with this number, capital M. And then you are always trying to say, OK, if your sample size is sufficient, and then you are in an under-parameterized regime, that's good. And then if not, then if you have less samples than the number of parameters, you are in an over-parameterized regime, and then you feel really unsafe, right? But now I tell you, OK, so it seems that there's a regime, over-parameterized regime, where we really feel unsafe about this recovery. However, I tell you now, look, there's a new number here. That is between 0 and the number of parameters. That is called optimistic sample size. I say, below this optimistic sample size, no recovery is possible. Because even though you really try to condense strongly, but still that is not enough. That number of samples are not enough. However, if you are able to just achieve number of samples above this optimistic sample size, I say, if the network can condense in a nice way, then that number of training samples is sufficient. OK. And then if you give me more samples, what happened? I said, OK, if you give more samples, I do not need to tune the hyperparameter so carefully, right? I don't need that strong condensation, right? And then I'm still able to recover the target. If I'm in this kind of under-parameterized region, I say, OK, even I tune this hyperparameter kind of so carelessly, still, because I have enough samples, there's still certain kind of a guarantee we get good solution. That is a new picture, right? That tell you, OK, in the over-parameterized scenario, still something good could happen. Okay, in practice, depending on how well you tune the hyperparameters, right? And then the samples, actually, the actual number of samples required for recovery can change. But whether the practical sample size can actually be close to the optimistic sample size, we need some more experimental evidence. So let's first look at this simple case where we are considering two-layer Tanh neural network. So for the two-layer Tanh neural network, so we prove that the optimistic sample size for the target actually depend on the minimum number of neurons that should be used to express the target. This number is here is a k. So here, this notation means the function space of k neuron network. So this means the function space of k-1 neural network. So this means the functions that can be expressed by k neurons, k Tanh neurons, but not k-1. So that is the space of this target. And then for these targets, you can see the optimistic sample size only depend on k, but not this small m. This small m is the total number of Tanh neurons for that two-layer neural network. So for example, we are considering the case where the k is just 3, and then this m is 9. So as what we see here, this d here is actually 6. So therefore, here the optimistic sample size is 21, and then the total number of parameters is 63. So since we mark these two locations, then we try to recover the target. So here, the x-axis is the number of samples we use in practice, right? From 1 actually to 63. And then, so the color means a testing error. So here, if it's really dark red, it means a testing error of 10 to the minus 6. It's kind of really low. And then we ask a question like, in practice, how many samples we need so that it gets to a sufficiently low testing error. It's almost like recovery. You can see the location is approximately here. There's a kind of a pretty high before this 21, but not so far after 21, you are able to recover the target very well. And then let's look at a more extreme case. Okay, the estimate is the same, but just we choose this small m to be 300, so that the total number of parameters become 2,100. Therefore, it's kind of, we can't actually draw this line. But still, we do the same experiment. Yeah. And then we see this transition period when it turns, the testing error turns from like large to almost 0. So it's still not far from 21. It's much less than 2,100. Yeah. Please.
What's the scale?
Yeah. So.
Like a kind of eyeball 21, 63 is about a third.
Oh, so.
That is close to 21. But for the next scale, it looks a little bit more logarithmic, right?
Oh, no. This is still 63.
Okay, I see.
This is 63, but no, I just said,
Okay, yeah,
because it's already red. Yeah. Yeah. So that's an experimental observation. Of course, you ask, you see this kind of, this bracket is well-tuned, right? So if you do not well-tune these hyperparameters, it could require much more samples to recover. So this tuning, yeah, please.
You have to reach condensation, right? This is why you say you have to well-tune.
Yeah, you should really tune these hyperparameters. Particularly condensation is important. You should make the network condense strongly in order to facilitate an earlier transition to almost recovery. Otherwise, it will lead to a much kind of delayed recovery. Yeah, so that is what happened in practice. Okay, now I think, yeah, please.
Then the obvious question at this point is,
Yeah.
is it easier to put more samples or to tune the hyperparameters well?
I would say, in practice, I would suggest just give it a little bit more. Yeah, because later you can, I would tell you that perfect condensation is almost impossible. There are reasons to that. But for some simpler models, for example, there's a matrix factorization model oh, I think the tuning is actually very easy. You just need to tune the initial variance to a kind of infinitesimal scale, and then you have guarantee. However, for these problems, no. For the neural network, there are further complexities to that. Because why there's a complexity is because, for example, there are many neurons that form in one group, right? And then you find that, okay, it needs to split. And then do they just split into two groups? Or actually, it could like diffuse so that incurs like a lot more groups. The answer is generally, locally, it's kind of diffuse. So that there could be drastic increase of the number of effective neurons. However, the further condensation could happen in the later stage. But it's just not like just growth 1, 2, and 3. It's not like that, right? And there are complexity to this condensation dynamics, so that you should never really expect perfect condensation. But what you can do, you just give it a little bit more, and also tune it carefully, so that combine these two factors is generally sufficient for you in practice. Yeah, please.
Sorry,
yeah, no problem.
So would it then make sense to say that if I wanted condensation,
Yeah.
I could just take, I don't know, a very large number of neurons,
Yeah.
and instead of trying to optimize on the WIs, I just pick some random ones. I just take a huge number of those,
Yeah.
and I try to do a sparse fitting of my function just by tuning the A's.
Yeah.
That's like a linear program, it should be global fast. And they should select a few of the weights.
Yeah.
Doesn't that then tell you a small network with a good initialization?
Yeah, I would say like you are now arrive at the algorithm similar to compressive sensing, right? Because you know in compressive sensing, we know that, for example, the coefficient is actually sparse. Therefore, we are kind of, for example, we can even use some like L1 kind of penalty to facilitate the kind of recovery of these sparse kind of coefficients, right? However, what I could say here that in practice, the performance of, it seems that these networks, in comparison to some algorithms you write down yourself, or even with this L1, it seems that the potential of this algorithm is actually better. Yeah, you can compare. Yeah, and there's some reasons to that. For example, there's estimates for the compressive sensing problem. So it says, okay, if you have k coefficients, right, it's called k sparse, and then the number of samples you require is k log m. So m is like the total number, the total number of bases you have, right? So still, it's like here, this estimate is like the k sparse, the number k here. So this number is really the minimum. There's no way to get below here, get recovery below here. But still, for the compressive sensing, we have like good complexity bound, but that bound kind of is like bigger than this number. So what I can tell you is it's bigger than this value. But whether neural network can actually break that bound or that, I think it's a kind of a very detailed problem. Probably I won't talk about now, yeah.
Okay, then to pick up on this log m factor, the fact that your practical well-tuned network is a little bit to the right, is that the log m factor that you see?
No, I didn't see it's a kind of a log n factor or that. I think probably later I just show you a little bit more. What we actually observe is that in certain situations, you are really able to get this one. Yeah, but it's just difficult to kind of characterize the condition. But in some really good cases, you can get there. It's not like there's an additional log m factor, but it's just depend on certain kind of situation. For example, in certain situation, what we observe is that you use some initialization, right? But still, there are kind of the initial angles could be different. And then there's a certain chance that, for example, among 100 different initial seeds, and then there's one or two that actually achieve this part. But there are more kind of initialization that requires a little bit more samples. Yeah, so it is more kind of delicate than the simple framework of compressive sensing. Yeah, and yeah, I don't understand the full details, and yeah, so therefore I can't tell you all the details, but still that's what we observe here. Okay, and then if now you say, okay, you have reason to believe that the optimistic sample size we estimated is actually relevant to the practice, right? Because you see that in practice it's possible to use a number of samples, not so many more than the optimistic sample size to recover. Then it's a time to really dive into a theoretical part to get some theoretical conclusions from this optimistic estimate. And here is a very important one. So this one tells you, okay, if you have a target that both a narrow network and a larger network can recover this target perfectly. And then you say, you are asking whether this wider network could be more sample efficient optimistically. And then what I tell you is that you should always expect that. It tells you, okay, the optimistic sample size of that target in the wider network is always upper bounded by the optimistic sample size in a narrow network, and in turn, upper bounded by the number of samples of the narrow network, number of parameters of the narrow network. Therefore, in practice, how you kind of actually empirically estimate the optimistic sample size, you just think about whether there exists a kind of a minimum network that you feel is able to approximate your target pretty well. And then the number of parameters in that minimum network should be a good estimate of the optimistic sample size for the target in a very wide network. And then now we go into the details of the proof of this theory. So how I'm able to prove this very strong result. It turns out that the key tool is this critical embedding operator, right? Amazing. So before, if you look at all this kind of definition, you don't see where I should use this kind of critical embedding operator I just tell you. But it turns out this is a key mathematical tool. Yeah, but why it's true is I can tell you that because this kind of critical embedding establishes a relation between the parameter space of the narrow network to the space of the wider network, right? It serves as a bridge. Therefore, for whatever this kind of relations between the network of different size, right, you can think about whether this kind of bridge really helps you, right, link some quantities between these two different, between network of different size. And before we go into the detail, I first tell you that there's a mathematically rigorous notion of the local linear recovery guarantee that's underlying the optimistic sample size estimate. So what it says is that, so what is a local linear recovery guarantee? We're saying that if we have a target function, f star, and then I'm trying to find the best possible local regime, for example, the best possible theta regarding this f star, so if we are lucky to initialize in its neighborhood, randomly initialize near its neighborhood, and then we say, okay, we just need a kind of a very small number of training samples to recover the target in its neighborhood or in its tangent function. So that is a notion of like a local linear recovering guarantee. So whenever we got an optimistic sample size, what I'm saying rigorously is that there exists a very nice neighborhood, right? This neighborhood has like a non-zero measure in all this parameter space. That is where I say it's kind of possible, right? Because it's not a measure zero. There exists a non-measure zero neighborhood of these best points. And then if you are lucky enough to initialize in that neighborhood, I can tell you, okay, so there's a certain number of training samples that is enough. That is a rank at that point. Okay, so that is the rigorous formulation or of this underlying this optimistic sample size estimate. So it tells you, okay, whenever your training data exceeds this optimistic sample size, then your target has this in-sample local linear recovery guarantee. And then now let's go to this how to use this critical embedding, or here we have a more general notion of critical mapping to prove this result. So there's an important lemma. This lemma says, given two models, if there exists a critical mapping P from model A to model B, and then there's this kind of inequality between their optimistic sample size. Okay, so this lemma is a key that tells you, okay, whenever you can identify a critical mapping between two models that preserves the criticality, and then using this mapping, we can prove the bounding relation between the optimistic sample size. Okay, so the critical mapping, the definition is here, output preserving and criticality preserving. It's just the same as the previous critical embedding, but just there's the previous critical embedding is a kind of linear operator, but here we don't really kind of require that strong kind of condition. So, but why is that? Or why these critical embedding can actually breach the optimistic sample size of two models? It is because the critical embedding, particularly the kind of splitting critical embedding, we can prove that it is rank preserving, or actually tangent space preserving. That means the tangent space, as I've seen in earlier slides. So here, this is a tangent space around the theta, where we span all its tangent functions, right? And then, if we use the critical embedding T to map this theta to the, let me write down the following. If we have a, there's a span, partial theta I. And then, so we kind of, there's a mapping. So this is around theta. And there's a mapping, give you a T theta, which is in a higher dimensional space. And then, the same thing, you span the partial. Actually, let me do this. It's kind of theta prime equals to T theta. And then theta prime I, and this as theta. Then this I equals to 1 to m prime. Okay, so if this T is the, for example, the splitting embedding in our previous definition, and then these two spaces equal to one another. So that's a key underlying this kind of relation between because the dimension of that tangent function space is our rank. Therefore, this critical embedding is also model rank preserving. So, and you can see, actually, this kind of preserving, for example, tangent space preserving property of these critical embedding operators. On the one side, it relates a criticality property. And on the other side, it relates to the model rank and also this optimistic sample size property. Therefore, it's a really kind of a very, very important tool that can help us prove the relations between the neural network of different size. Yeah. Oh, okay. Yes. So Okay, okay. Yeah. And also, since we identify, okay, as long as we identify certain kind of critical mapping, and we can prove this kind of relation. And what kind of critical mapping we can have. So from the previous embedding principle in width, we know that between like the narrow network and the wider network, we have this kind of embedding, and you know how to construct them. And also, because I've also mentioned the embedding principle in depths, between networks of different depths, there's also this kind of, we can identify this kind of critical mapping. And therefore, so previously we used this kind of critical embedding to give you the embedding principle in width and depth that tells you, okay, the loss landscape of the neural network contains all the critical points of all narrower or shallower neural networks. That is what we use these two embedding operators to show. But now, with this previous lemma, with this kind of critical embedding operators, we are able to say that whenever we increase the depth of the network or we increase the width of the network, the optimistic sample size never increase. Yeah. And that is a key information we have from all these theoretical results. And that justifies the previous empirical observation that we should never worry about the performance of the neural networks if we tune them properly as we increase its size, right? You should always trust a very large network if you are able to tune it properly. Let's start our second part. So now we have a really nice definition of the optimistic sample size, and we get some good results regarding the impact of increasing the width. But there's a very important part that is about the connection. So we want to use this optimistic sample size to really help us understand the impact of this connection. And actually, the first lesson we've ever learned with this success of the neural networks is that for the imaging data, we really need to use convolutional neural networks. And using fully connected networks does not really help the neural network excel from other methods. Yeah. Therefore, like in 2012, the AlexNet, as the deep convolutional network, like give us the first convincing story that the neural network, the convolutional neural network, are the almost the best architecture we could ever think of for the imaging data. And now, so let's think about the following setup. We try to understand the sample efficiency regarding, for example, a convolutional neural network with convolution, with weight sharing among different kernels. And also, we can consider a convolutional network with only local connection, but no sharing among all these kernels in different locations. And also, a very naive, fully connected neural network where all neurons in the previous layer are linked to the later one. And then you can ask, if we are considering a target that is in the space of the convolutional neural network with like weight sharing. So therefore, we can ensure that for all the functions in this space, all these three architectures can express them without any difficulty, right? Because we are always focusing on the functions that can be expressed by all these three architectures. And then there's this kind of like 1, 2, 3, like 1 to n. That means the intrinsic complexity means how many neurons or how many kernels you need to use to express your target, right? And then later you can see all these kind of estimates with different kind of architectures. What I need to ask you to pay attention is that here there's a coefficient of k in the CNN, normal CNN. Then without weight sharing, what happened is that there's a s squared plus 1. So where does this s squared plus 1 comes from? So here there's a convolution kernel size. So the convolution kernel size, if there's no weight sharing, and then there's an additional factor here. And then if you make them fully connected, and you can see that there's a d squared plus 1, which is an input dimension. For example, like 28 by 28 for a certain imaging task. So there's a huge increase in the optimistic sample size regarding a particular class of targets that all these networks can express. And then if you look at a very specific example, when we see that if our input is this MNIST data, which is like 28 by 28, and then we are considering a target which is like a k-kernel target with a kernel size 3 by 3. And then if we estimate the optimistic sample size with the convolutional neural network, so that is the size, 685K, without sharing. So you can see there's 10 times more samples required. And with a fully connected network, so there's additional 100 kind of times more samples required, even for the optimistic sample size estimate. So, but you can see here, it depends on K, which is the intrinsic complexity of a target, but not M. So what is M? M is a number of, it's like width. It's a number of kernels you use for fitting. So that is, the M can be large, but all these optimistic sample size only depend on K, but not M. However, the connectivity, if you incur this unnecessary connectivity, then you always need extra samples to help you constrain all these unnecessary connections. So that is a lesson we have from this story. And then there's a very simple experiment. What happened is that we use a network which is generated by a CNN, the normal CNN with sharing. And then for this CNN, this target exactly match the complexity, or this model, this CNN model exactly match the complexity of the target. And then, so you can see a very nice agreement with this translation to red with this optimistic sample size, which is yellow. However, if you fit the same target with CNN, but there's no sharing, what you need is this slightly delayed, or it's a higher optimistic sample size, because you relax the degrees of freedom. And further, if you use a fully connected neural network, right, you add more connections, the optimistic sample size further increases. And still, you can see there's a delay in this recovery that is, matches with this yellow line. Okay, so that tells you, in this very simple example, if we really know that this function can be very well expressed by a convolutional neural network with sharing, then you should not really consider the CNN without sharing, and even the fully connected one will be even worse, because all these things that are zero, or all these connections that are zero, but you need extra data to actually tell the neural network that they are actually zero. They are not related. So you need more samples to do that. So that is experimental result. Okay, so now let's really look at the, in which sense the deep neural network model are so special. Or the network that with nonlinear parameterization or nonlinearly parameterized by a neural network that is kind of very different, has very different properties. On one side, actually adding the connection, this connection side is actually traditional in a sense that whenever you add unnecessary connection, it becomes less sample efficient. So that's a lesson we already know from previous modeling. For example, polynomial models, we already say you must ask whether really the higher order terms are necessary, right? Otherwise, you should never really add the higher order terms. So in the connection part, it's the same story. It's also like the outcome research. However, regarding the width part, it's a different story. The width part, it tells you, okay, increase the width is actually efficient, or preserve the sample efficiency. You don't need to worry about the generalization part. So you see there's a kind of a different part, but you can see both of the network you increase the complexity, and you increase the complexity to both like with 24 parameters, but their generalization behavior can be completely different. Okay, therefore, if you only think about, okay, the number of parameters is an indication of generalization, then I tell you it's not. The connection is very different from the number of neurons or the width of depth is very different. Okay, there's also this kind of what can you learn from all these theoretical results? So when you use these neural network models, and then you can freely increase the width, actually also the depth, because we have embedding principle in depth. So without worrying about sacrificing the sample efficiency. But you should really refrain from adding connections. For example, you are kind of trying to solve an equation with this like local Green's function. And then you shouldn't consider a kind of very global network with very global connections. Okay, so you should refrain from adding connection unless they are really necessary. And then there's also an interesting analogy with the development of the brain of the mammals. For example, in the mouse, we have like 10 to the 8th, the number of neurons, and the connections per neuron is like 1,000 to 10,000. In our human brain, the neuron number are increased by it's a kind of 1,000 times. However, the connections per neuron remains in a similar level. So you can see, even in the scaling of our brain, it seems that the network prefers to add neurons instead of the connections per neuron, right? And it's just an interesting observation. But of course, in neuroscience, we can never explain this phenomenon or never have like a functional kind of understanding, because we always need to admit, okay, that's a biological fact, right? We don't know where it comes from. It's just there's a fact. If your modeling does not obey this kind of fact, you are not modeling the real brain, okay? But now, from the artificial network, we see something different. We see that increasing the connections, we always ask, okay, whether they are really necessary. But increasing the number of neurons, it seems that we don't need to ask any question, right? We just need to say, okay, probably you want to dealing with more complicated data, right? You want more approximation power, but you don't want to sacrifice the generalization or sample efficiency for the simple data, right? And then you just increase the width, or increase the number of neurons, or increase the depth, but don't increase the connections unless you really see there's a reason in that. Okay, and after all these kind of difficult kind of results regarding your networks, now let's relax a little bit to use the optimistic estimate for simpler models. So the first model is a linear model, right? Okay, we say, okay, we can estimate the sample size required for recovery for these kind of difficult models. But what happened for simpler linear models? The answer is, for the linear models, our optimistic sample size recovers the classical results. That means even considering the case in the best possible scenario, still you don't improve the bound. In the classical estimate, you say, okay, as long as I have like I have m parameters, when I have m samples, it's enough to exactly recover all these parameters, right? And then even thinking optimistically, still it's m. There's no way to recover below this m. Okay, so in that sense, our optimistic estimate is on the one hand, agree with all these classical results. On the other hand, it's a kind of an extension, and it's a powerful extension allowing us to deal with nonlinear models. Okay, so there's actually there's a theorem regarding that. Linear models cannot recover targets under overparameterization. Okay, but this is an intuitive statement. In our paper, there's a more rigorous statement of that. Now let's consider little bit more complicated model, right? So people sometimes call it like deep models. So why is deep? Because instead of like having this AI xi, we have this AI square minus bi square, right? So we have a nonlinear parameterization of linear functions. So what do we obtain? So from the optimistic sample size estimate, so if the target is a k-sparse function, it means that there's only like a k coefficient, k nonlinear coefficients regarding all these x in different dimensions. And then the optimistic sample size gives you the number k here. Okay, this gives you the following picture. Even with this nonlinear parameterization, so there's no way to recover the target below with the samples below k. And then all that realistic is somewhere between k and this small m. In practice, what happened for this simple model? Actually, we have a full understanding regarding, well, it's like in the 2019, it's around that place. We have full understanding that this problem actually implicitly, through the gradient-based training, starting from infinitesimal initialization, it implicitly minimizes the L1 norm. So with that equivalence relation, and then we know that the sample size required for a recovery target is a k log n. So just from the theory of compressive sensing. And you can see it's still much closer to k than this m. So our optimistic sample size is kind of really like at the lower bound side. Okay, so this a kind of a simpler model. And there's this model. This model, I assure you, there's no theory that tells you if you just run the gradient descent from infinitesimal initialization, what you could learn. In practice, if you really run the gradient descent on this model with infinitesimal initialization, you can observe similar phenomena as this previous model, right? But just you are not able to prove that because the dynamics is much more complicated than this model. And then, still, you can do the optimistic sample size estimate without any difficulty. And then the answer is still k. So what it implies, it still prefers the sparse targets, right? If your target is really sparse, then it tells you, okay, less samples are required. Okay, so, and you can try yourself because it's a very simple model. You just try yourself to see whether your kind of empirical result agrees with our optimistic sample size. And there's also this matrix factorization model. So what is a matrix factorization model? We try to model one matrix by the product of two matrices. So in which sense this model is useful? So it is often used for matrix completion. For example, so in the next Netflix problem, where we have lots of users, it gives scores on different kind of movies, right? But how can we predict for a new movie, what is your rating, right? How I predict that? If I predict, okay, there's a new movie, you should give it score 5, right? And then I just recommend it to you. That is a Netflix problem. So the Netflix problem is actually a matrix completion problem because I already have lots of observations that certain users rate certain kind of score for like a variety of different movies. It's just that this matrix is not complete. If we are able to really get a very accurate completion of that matrix, and then that makes big money. It used to be $1 million price for the kind of a best algorithm. And I think it's at the time of 2010. And later it's shut down because of this privacy leakage. They actually find that from that data set, they can identify who gives this kind of rating. So this kind of rating can sometimes be sensitive. Yeah, I don't know if you have this idea. So you watch a specific class of movies, so that reveals something special about you, right? So it's that kind of privacy leakage is actually kind of huge problem. Later they stop that. But what we observe is that in the top algorithms, they use something weird. Some of these top algorithms use this factorization model to parameterize this whole matrix. And then, since we have certain kind of observation, we just run. So at that time, it's not gradient flow. They just try to find for example, the kind of different kind of eigenvalues and eigenvectors. Just one by one, find a kind of gradually higher rank approximation to this observation. But later, we find out just running gradient descent from a infinitesimal initialization, these models seems to be able to really give you nice low rank approximation or low rank completion to the problem. Okay, so that is how we use this matrix factorization model to complete for matrix completion. And then we can do the same thing of all these optimistic sample size estimate. We call something called rank stratification, which is given you certain A and B, compute the model rank at that theta. So the model rank depends on the rank of the A matrix and also the rank of the B matrix. These are matrix rank, so RA and RB. So if RA and RB, both of them are kind of, for example, 0 rank. For example, both A and B are 0, then the model rank is 0. If both of them are 4 rank, then the model rank is a D squared. This model rank is a D squared. It's also the 4 rank. So if we think about the optimistic estimation, and then what it tells you, depending on the rank of the target function, and then the different number of observations are kind of required. That gives you the optimistic sample size. So for example, later, let's look at this specific result. For example, our target function is a 4 times 4 matrix. And then these are the optimistic sample size. In total, there are 16 kind of observations, entries you could observe. And then I said, if your target matrix is rank 1, and then at minimum 7 entries is enough for you to recover that target. And then if it's rank 2, then 12 entries should be recovered. 12 entries should be observed. And then we kind of checked this kind of prediction on some like a particular or 8 different matrices. The first 2 with rank 1, and the later 3 and 4 with rank 2, rank 3, and rank 4. And then we kind of increase the number of observed entries gradually and see whether it can have the transition at the yellow line, which are optimistic sample size we derive. And you can see in this model, we can do a perfect job. And then now, so I always emphasize that here, infinitesimal initialization is important, right? It's a similar story as before. Here, actually, smaller initialization also leads to stronger condensation. But the meaning of condensation is a little bit different from the neural network, is that as long as these matrices of the A and B are low rank, and then they are at a condensed state. How can you tell? Just by computing the model rank. The lower model rank, you have the stronger condense, you should so they are at a stronger condense. So that is just from this kind of estimation. You know what does it mean by condensation. Just lower rank of this A and B matrix means stronger condensation. Okay, and then if we gradually tune this initialization scale up, for example, sigma from 10 to the minus 5 to 10 to the minus 1, what you observe is that the kind of transition gradually kind of delays, right? And even you have a very large initial variance, 16 is definitely enough because at total, there are 16 entries, right? But if you really want to recover them with kind of minimum number of observed entries, then you should really start with very small initialization. So that is a key to facilitate condensation so that to help the matrix factorization model recover the low rank get a low-rank completion of the problem. Okay, so the conclusion is that the success of the fitting or getting the perfect recovery at the optimistic sample size actually depends on the initialization scale. Yeah, please.
This is quite interesting. I'm wondering if you consider computation time.
No, infinite. It's always like infinite. I chance,
Right.
yeah.
But in practice, you don't want to run a code for infinite time. And if I remember correctly from what you said in previous lectures,
Yeah.
the smaller the initialization at the beginning,
Yeah.
the longer it takes, because you're basically close to a saddle point, zero is a saddle point.
You are right. Here, there's a very special behavior that is saddle-to-saddle dynamics, where it increases its rank one by one. It's always like this if you start from infinitesimal initialization.
Right. But
Yeah.
then if I start from, if I take a small initialization, I would expect that it would take longer
You're right.
to escape the first bit.
You are right. That's right.
And so maybe there's an optimum balance of how many samples and how big the initialization needs to be if all I want to do is minimize my training time.
Yeah. So you are absolutely right in the sense that so small initialization, strong condensation is very good for complexity control. It can do a very perfect job, right? However, if you control the complexity so well, that means throughout the training, the complexity grows so slowly. That is, it takes much longer time to grow to a sufficient complexity that the optimization could suffer. Therefore, in practice, you may want to achieve a balance. For example, you want to first guarantee I have a perfect recovery, and then the lesson is you should give more samples, right, than the minimum, than the optimistic sample size. You just give it more. And then you could choose a bit larger initialization, but still expect recovery. I think that's a lesson here. So in practice, it's always like a balance between like different sides.
Right, so if you're running for this example, what does the optimal fall?
Oh, you mean here, the optimal, so it's like 10 to the 5, 10 to the 4. It's a kind of a...
But if you take into account computation time, is it not better to maybe take 14 samples and initial sigma 10 to the minus 3? So you have a very small error, but maybe you train faster?
So,
Considering a few more samples doesn't increase the cost of the optimization too much, but
so
just make the saddle point faster.
you see here, experimentally, I usually do not like dive into that kind of complexity in a sense that I think it's always my priority first to understand the extreme case. For example, I always let the kind of training goes to infinite time in order to understand its limit, right? I never early truncate to kind of make it less powerful. I always want to give it sufficient training time to see its maximum power to recover the stuff. So in that kind of, with this kind of motivation, I think I kind of don't have much experience about this kind of balance. Yeah, so I think probably later, because we already have this understanding, so it's better to later understand this more kind of practical balance between things. Yeah. Yeah, so increasing the data size beyond the optimistic sample size enhances the tolerance on tuning. I think if you don't trust your tuning capability or you want it to train faster, and then just give it more data, right? You should always keep that in your mind. In many scientific problems, if it's possible, just get more data. It could kind of ease your time for tuning. Okay, for the later part, it's about, so you can see optimistic sample size estimate is an elegant framework. However, if I just write down a model, you may feel it takes too long to understand what it's good for, because it seems that you need to go through all this detailed computation of the dimensions of this tangent function space to arrive at optimistic estimate. But I say, don't worry. If there's a special symmetry in the model, we can get a very quick estimate. So what's the key symmetry that helps us estimate the optimistic sample size? So it turns out to be the permutation symmetry. So what is the permutation symmetry in our neural network? It says, okay, in one layer, in any layer, so different neurons, for example, neurons with index j and j prime, if you permute their index, and then the output function remains the same. So that is permutation symmetry. Okay, and then you can prove the following theorem, that permutation invariant manifolds. So what does permutation invariant manifolds mean? So you have a manifold, and then you permute these dimensions, but it's still give you the same manifold. And then that is called permutation invariant manifold. For example, if you consider permutation of j and j prime, then that manifold have the constraint of all these input and output parameters regarding the j. It's exactly the same as the input and output weights of the j prime. If they are equal to one another, then that gives you a permutation invariant manifold. And the result tells you that these are invariant manifolds of gradient flow, regardless of the training data. So these invariant manifolds are only determined by this neural network architecture. Okay, so as long as you have this permutation symmetry, and then you can find invariant manifolds, and at the same time, these invariant manifolds for neural networks are equivalent to smaller networks, because you can combine these two neurons, right, so that the effective number of neurons are actually less. And then on that invariant manifold, it's actually, so the neural network mimics a smaller network. Therefore, if you can really able to constrain all the training dynamics on that invariant manifold, then the optimistic sample size should be no larger than the smaller network. So that is a basic understanding. So you have a really big network, but there are lots of these lower dimensional invariant manifolds there that are equivalent to smaller networks. Therefore, if you are lucky, your training are lucky to be kind of attracted by the invariant manifold of right complexity, then it's at least as good as these smaller networks. So that is a basic understanding. Okay, so whenever you have certain kind of index that has permutation symmetry, you can say, okay, if I increase these dimensions, so it could be sample efficiency preserving. And also, you could expect condensation. And what's the use of this kind of intuition? So it helps us directly have some understandings about the transformer. Okay, so if you look at the expression of this transformer, there are kind of many different dimensions you could consider to increase so that you get a larger transformer, right? In many of these large language models, you can always see the experimental result regarding like different size of transformers. So how they increase the size? So these are the kind of actually the dimensions they actually consider. For example, the embedding dimension, attention matrix dimension, or heads dimension, right? The number of heads. So what's special about this kind of dimension? You can see this dimension has permutation symmetry. So meaning that if you kind of permute the index of different heads, it remains the same transformer. It remains the same output. Okay? If you change the dimension of the embedding space, it's still give you the same result. And the attention matrix dimension, which is like in between this WQ and WK, and then still this permutation does not change this whole matrix. Okay? Therefore, the optimistic sample size estimate this kind of general result regarding the symmetry and the sample efficiency tells you you can scale all these dimensions to a very large value without worrying about the sample efficiency. Okay, so that's something we can say about the transformer. How many of you know this CAN, Kolmogorov-Arnold network? How many of you? Yeah, it's actually like half. And you can see that there's once a while people are just feel, okay, probably this is a very powerful new architecture, right? And it is backed up by this famous guy in the history called Kolmogorov and Arnold. Probably there's something amazing, right? And it's a kind of the architecture design from the first principle. by Kolmogorov and Arnold. But all of these arguments are actually misleading. But now let's just look at these neural network or these models without any prior. I say, okay, it just gives you a nonlinear parameterization of a function space, right? And then for these kind of nonlinear models, we can ask about the sample efficiency issue, right? If we increase the complexity of that model, whether we should worry about overfitting or not, that's the question we are trying to ask for these kind of models.
Sorry, can you recall what Kolmogorov and Arnold state?
Oh, representation theorem. What they said is that in a unit cube, in a d-dimensional unit cube, we have a continuous function. For example, in a 0 to 1 d-dimensional cube, we have a kind of a continuous function. So this, for example, the f, there's a f star that belongs to a continuous function space on this kind of unit cube. And then it says, it asks the following question: can we express or represent this f star by the univariate functions, the composition of univariate functions? So the final answer is there is I equals to 1 to, I forgot this, whether it's 2D or D. It probably I think probably it's 2D, but just correct me, I forgot. But there's a finite number, this phi I, and sigma j equals to 1 to D, phi I j, x j. Xj. Yeah. So that is the general result. So just pick an arbitrary kind of f star that is continuous on this unit cube. And then I said, okay, look at this kind of function here. These both phi I j and this capital phi I, they are univariate functions. And then just with this finite number of these functions and with this composition, you are able to represent this f star.
Okay.
So
it says that such functions exist.
That's right.
Doesn't say,
and finite.
Okay, but this is an identity. It's not an approximation theory.
It's representation.
It's
Yeah. But this representation theory, you can see, so these univariate functions are not necessarily continuous. If we restrict all these univariate functions to continuous functions, you cannot prove that. There are worst cases where these are not continuous. Yeah. So that's something we know about this Kolmogorov-Arnold representation theory.
How can they be discontinuous if the output is continuous?
Actually, so I think I don't really go into this kind of construction, but that is, we know there are cases like that. So you see, if really we are able to use continuous functions to approximate, and finite many, to approximate any kind of f star, you see it's very, very powerful, universal kind of approximation result, right? But it seems too good to be true. Yeah.
But now you could apply, at this level, you could apply Sibenko's, for instance, theorem of universal approximation to each of these terms, right? So for
but if some of them are not necessarily continuous, that's a problem. Yeah, because when we talk about universal approximation, we are considering approximating continuous functions, but they are not necessarily continuous.
You can also approximate L2 functions, or not?
So you should be careful about what kind of approximation you want. Yeah, and then you probably can achieve something. And that is their argument. Okay, although if if they are actually use this kind of discontinuous kind of things, we can use finite many to express f star. But actually, what we can do is to use continuous one. And then they said, okay, what we do is to increase this number. For example, particularly this kind of D, right? They can increase these numbers, and also you can increase the depth so that there could be further compositions. And then they expect that, okay, if we do this kind of modification, we kind of avoid this issue of the discontinuous issue of this Kolmogorov-Arnold representation theory. So that is how they arrive at this kind of Kolmogorov-Arnold network. Yeah, just use these continuous things and with a little bit larger size to approximate things. And then, yeah, so, yeah. Then if we look at this model, we say as long as we have certain dimensions that is permutation symmetric, and then we can increase the size of that dimension without worrying about overfitting. And this index I has this permutation invariance, or has this permutation symmetry regarding this I. It's like the width of the neural network. We said, okay, you don't worry about that. But there's an additional term. For example, for all these univariate functions, they use a spline. They use this kind of spline to parameterize these univariate functions. However, we know that these kind of CI, these things do not have permutation symmetry, right? If you permute these kind of coefficients of two splines at different locations, you get different things, right? Different. Therefore, so our results suggest that increased G could reduce sample efficiency, but you need extra careful kind of estimate. But this result is kind of direct. But this result, you need to kind of have a little bit more careful computation. But I tell you, okay, increased G, the optimistic sample size should increase. And then what happened in practice? Okay, so, and for the same network, I have like different ways to increase its complexity. The first is to increase its small m, which is indicated by these red lines. So you can see the training error goes down, and the testing error always goes down when you increase the parameter size. And you don't worry about overfitting. However, if you try to increase the number of grids, and then what happens is like this blue lines, your training error, this dashed line goes down. However, the testing error goes up. Yeah. And if you are careful enough to look at the experimental result in their paper, you can see that there are results that with very fine grids. And then their results are actually very poor. But they never really discuss this phenomenon carefully. Therefore, I can tell you, okay, the CAN is kind of a little bit different architecture than the fully connected network. And then we need to kind of use this optimistic sample size framework to kind of redo this kind of all these estimates to see what kind of properties regarding, for example, this kind of spline parameterization that is induced to the problem. And I say you should be really careful about this part. And also, there's a kind of empirical kind of experience that these kind of Kolmogorov-Arnold networks are actually very difficult to train. It's not impossible, but it's just so difficult. Yeah, but why is that? I don't have an exact understanding. But I can see that, you see, these width dimensions, because of the embedding principle, are actually good. Right? Because somehow, when you increase the width, there could be more descending directions, right? However, for this kind of a parameterization, I'm not sure how it interacts with the former part. Probably there are something that kind of makes the training a little bit more difficult. Yeah. And the last part, there's also kind of an empirical estimation because we know, although I give you a very kind of nice framework to estimate the optimistic sample size, but in practice, you don't really know your targets, right? How to estimate the optimistic sample size for the problem you have in your hand, but you don't have the expression of your targets. Then comes to the empirical estimation and some application. So what I do is like there are these kind of problems, right? I just showed to you, we call that anchor function, where we present all these kind of numbers to a transformer and ask the transformer to learn all these targets, right? And there this 1, 1 corresponding to +5 or all this different kind of stuff. And then, so if I'm trying to estimate the optimistic sample size for certain tasks, for example, for this kind of task, I have like 14 different kind of anchors with underlying composition rules. And then I ask, what's the minimum number of samples required for the network to actually learn all these kind of results or learn all these kind of mappings? And then what we do is to do this very careful experiment. The x-axis is a training data set. We kind of gradually increase the training data set, and then to see on which kind of data set the performance goes to, the testing accuracy goes to almost 1. And then there are some of these important hyperparameters we should be careful, because these parameters, we know that they could facilitate condensation. First of all, it's an initialization scale, right? This initialization scale, particularly in some kind of range to a smaller size, it could strongly facilitate condensation. And also the learning rate. What we observe in transformer is like larger learning rate actually facilitate condensation a little bit larger. But still in practice, you need to turn it carefully. And weight decay. We observe that larger weight decay leads to stronger condensation. So therefore, we tune all these 3 kind of things in hope to find a region where it can give us the kind of best possible hyperparameters. And then the final result is that you can see it's like 1,800. It seems that you just give them 1,800 kind of observations, and then if you tune all the hyperparameters correctly, and then you obtain a very good result. So that is how we get this empirical estimate of the optimistic sample size for a certain task. And then there's a interesting kind of thing. So we can always, for example, we can design this kind of task so that there's no composition, right? I just give them certain tasks with no composition. And I ask how many samples you need to see in order to predict all these 16 different anchors where there are no correlation. They are perfectly independent. And then I also ask if they have composition rules. Does it mean we need like less samples to recover? Okay, here are the results. So the x-axis is the actual number of samples. And then if the neural networks say, OK, for each of the anchor, I try to learn it independently from others, right? And then that is the complexity of the task. So the number of anchors means the complexity. And then as the complexity grows, we should expect we requires more and more samples, right? More complexity, more samples. And then if all these anchors are kind of random, means that their operations are independent to one another. There's no correlation they could employ. Then this red line is a slope. It's a kind of the number of empirical optimistic sample size increases. And however, if we consider we have this inferential structure, means there's a composition structure underlying, then you see there's this kind of green lines. Actually, what you can see for 4 times 4, the total 16 different anchor problem. So it's the number of samples required is actually the same as 2 times 2 random kind of tasks. So that means it seems that the complexity for the transformer, that these 4 times 4 kind of 16 different anchors with composition structure is the same as a 2 times 4, 2 times 2 random anchors, right? And this result, I think it tells you these transformers are really good for these tasks with composition structures. Okay, so that's the, yeah. That's the end of this story. So there are more details, but I just stop here. So, and what does less optimistic sample size mean? It actually means your task is more or matches better with your architecture, right? So that's why like a lower optimistic sample size is always good. And what I tell you today is that whenever you obtain a nonlinear model, you should not just look at this total number of parameters, say, okay, whether it's under parameterized or over parameterized, but you should really consider there could be some optimistic sample size that could be much less than the total number of parameters that is underlying. And then if you do not have enough samples, you are hopeless to recover the target. But if you give it more than that, with proper tuning, you have a good chance to recover the target even in the over-parameterized regime. And then the ways to improve sample efficiency, there are two ways. First is to reduce the optimistic sample size. For example, if you build up a better architecture, then your target could be expressed by a much smaller size network. And then it means you could actually, with a better architecture, this optimistic sample size is reduced. Okay, and that requires optimizing the architecture. For example, if there's a symmetry, you build that symmetry to your architecture, and then definitely you reduce this optimistic sample size, right? And then the second is get close to this optimistic sample size. That requires to optimize these hyperparameters carefully. For example, the smaller initialization scale, larger weight decay, and larger learning rate. That could be the trick for transformers. But of course, if not a transformer, I think you should be a little bit careful with later two. But the first initialization scale still is a very, very important kind of technique. And okay, I think it's now to conclude all these 5 lectures. So the title is like Towards a Mathematical Foundation of Deep Learning. And with all these 5 sessions, I tell you about the general situation of deep learning. And I tell you about 2 phenomena, which is frequency principle and condensation. And we spent 3 lectures on condensation, which we gradually covers the regime of condensation, and also its impact to the reasoning part, and also what kind of loss landscape is actually underlying the condensation. And also today, we cover the generalization part, how to understand its generalization advantage. And so the global dynamics remains a missing piece, and we are exploring that in the next few years. And now, if there are some final questions, or what you actually learned, now we just revisit all these 4 problems proposed by Liu Breman to see if you can have a better answer. First, why don't heavily parameterized neural networks overfit the data? You can answer this in 2 ways. First, by frequency principle. You know that, okay, if the target function is dominated by lower frequencies, and then you don't expect it to overfit, even you have tons of parameters. And the second answer is from the perspective of condensation. You see that, okay, the neural network tends to condense, right? Try to use some minimum complexity to explain the data if you tune the network to a very condensed kind of behavior. And then both of these help the network prevent overfitting. And the second, what is the effective number of parameters? So this question is just comes from the observation that it seems that we don't need as many samples as a number of parameters to fit the problem. And then, so probably there's the effective number of parameters is less. So our optimistic sample size estimate give you exactly the answer to the second problem. Okay. And the third, why doesn't backpropagation head for poor local minima? So there are 2 part of this answer. The first part is that there are not many local minima there, because as you increase the width, so they could become strict saddle point. And then why they don't head to a poor place, because there's an implicit bias that prioritizes our lower frequency stuff or these condensed stuff. So they don't go to this highly oscillatory part. Okay, and the last problem, why should one stop the back propagation and use the current parameters? Because we have all these kind of preference throughout the training, right? And then if there's some kind of a perturbation that does not fit the structures of the pattern of your task, and then you should always expect the neural network first extract this part with patterns, and then go to this, and then move to the noisy part, and then you can stop. So the final comment is that you see these lessons from Leo Bremen, I think few people really heed to the lessons. He said our fields were better off with far fewer theorems, less emphasis on fetish stuff, and much more scientific inquiry. However, I think particularly in the field of statistics, I think almost none of people actually heed to his lessons. However, you can see this kind of understanding is very important. So what my suggestion is just suspend your framework, dive into the problem, and then you should also experience between theorize, because there's an object you've never seen before. You should have some experience, do more experiment to observe what is there, and then theorize stuff. And so what I see now is there's a dawning of the mathematical foundation of AI. So what we are now, we suspend all these kind of existing frameworks, and we accumulate more and more pieces, as I've told you throughout all these 5 lectures. It's just more and more pieces. They are very solid pieces. And then I think there's just a little bit more missing pieces to uncover. And then we should see there's a more complete picture emerges from that. And I want to thank you all, and just give you this kind of advertise. This is a Chinese version of this, we call the introduction to the deep learning phenomena. So, and you can find the PDFs with this code, and you can also track our works from my personal web. And thank you all.